Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series intended for the BSc Physics Honors students, and we go through a chapter on wave optics in the paper on Basic Physics 2. This is the lecture number 15 coming under wave optics, and in the present lecture we will be covering the following aspects. So the contents are Young's double slit experiment, wavefront division, bright and dark fringes, optical path difference between the waves at a given point, and finally the fringe width. The important point that we address now, from the Young's double slit experiment, we understand that the phenomenon of interference can be explained only by wave optics, only by considering waves as though they are made up of light waves. And I want to reassert that the corpuscular theory which was propounded by Newton is completely wrong. It can not be used to explain the phenomenon of interference. Having said so much about interference and having talked about the origin of bright and dark bands, you got a bright band, dark band and so on, one is tempted to ask the question, what is the distance that separates the two successive bright bands? That is called the band width or the fringe width. The distance separating the two bright bands or the distance between two successive dark bands, both should be equal to one another. And so in this lecture we will see the mathematical aspects as to how to arrive at the expression for the band width or the fringe width, which will depend upon the wavelength of the light source, the monochromatic source that you have got here, the wavelength and the distance separating the two sources and the screen. All these things will come in the final expression. That is what we are going to obtain in today's lecture. And once again we have got a light source, there is a source S1 here, and this light coming from here, it is passing through the two slits. The light passing through the two slits, they act as two coherent light sources. Light emanating from the two coherent sources, they interfere with each other. This is the region where you see the waves are meeting or interfering with each other. Because of the interference, as we saw in the earlier lecture, on the screen you will be having a bright line, dark line, bright line and so on. So you got a bright band, dark band, bright band, dark band, and most of you would have done the experiment in the laboratory using the sodium vapor lamp. You would have seen the bright line, dark line and so on. So these are the bright and dark bands which are obtained by the phenomenon of interference, wherein the light coming from the coherent sources, they interfere. So, as I told you in the last lecture, due to constructive interference, you will be getting a bright band, or due to destructive interference, you will be getting the dark band. So, the experimental arrangement goes as follows. The primary light source is a monochromatic source. The primary source that you got here is a monochromatic source. So, you should use the monochromatic source. These two act as two light sources of, in the important point, two coherent sources. Okay. So, it is generally a sodium vapor lamp, as I told you just now, emitting a wavelength of 5893 angstrom. That is the first source. It is passing through the two slits. They act as coherent sources. The light is not coherent because the light is coming from different parts of an ordinary source. To make coherent sources, the light is made to pass through the two slits B and C. From a single source, the same source, the light is passing through the two slits. That is the reason why you say that the two sources are coherent sources, because it is obtained from a single source. The cylindrical wavefronts which are produced from the slit A, the primary light source, that is A is the first point, that is the S1, which fall on the two narrowly spaced slits B and C, which we have shown as S1 and S2. The cylindrical wavefronts are produced from the slits, they overlap. What I mean by cylindrical wavefronts are the wavefronts, right? The wavefronts, the wavefront that is coming here, wavefront that is coming here from S2. Similarly, the wavefronts coming from S1, the cylindrical wavefronts, they interfere, and depending upon the condition, crust meeting a crust or trough meeting a trough, leading to constructive interference, or on the other hand, if a crust meets a trough, that will lead to destructive interference. That means the screen will appear to be dark. That region where there is destructive interference, there will be darkness. The two sources of light should emit continuous waves of the same wavelength at the same time period. That is, the sources should have same phase coherence. The sources should have phase coherence. That means phase coherence means what? That is, the phase difference between the two sources should be 0 or what? Or 2 pi, as we saw in the earlier lecture, 4 pi. So, a phase difference either 0 or 2 pi and so on. The two sources of light should be very close to each other. As I told you in the last lecture, the distance separating the two slits is very large, then there will be the two sources will not be interfering. There will be no interference pattern at all. So, the two light sources which you are talking about should be close to each other. The waves emitted by the two sources should either have 0 phase difference, that means no phase difference. The sources of light which emit light waves continuously the same wavelength, right? The wavelengths of what are the conditions for, when will you call the two sources to be coherent sources? They should emit light the same wavelength. And time period. Time period means what? The two waves should meet in such a way that a crust meets a crust or a trough meets a trough for having constructive interference. That will be 0 phase difference or a constant phase difference, that means 2 pi, 4 pi and so on. When the two light waves superpose with each other in such a way that the crust of one wave falls on the crust of the second wave, that will lead to constructive interference. Crust meets the crust, or a trough should meet a trough. That is what I am showing in the bottom. A trough of the first wave should meet the trough of the second wave. Then also there will be constructive interference. Either you will have A plus A or minus A plus minus A, minus 2A. Both cases there will be constructive interference. On the other hand, there will be destructive interference, as you will be seeing a bit later. So, for constructive interference, the path difference between the two waves is m lambda, and m will be 0 or lambda or 2 lambda and so on. So, m is the order 0, 1, 2, 3 and so on. So, path difference should be integral multiple of lambda. For what is the condition for constructive interference? the path difference should be integral multiple of lambda. That is important point. N is an integer, right? You get bright and dark fringes on the screen because of the constructive interference as well as destructive interference. So the theory that we are going to go through is goes as follows. You got two light sources S1 and S2 emitting waves at the same wavelength and same phase, and let's try to find out whether we get brightness or darkness at a given point P. You choose a point P, some point here, right? The point P here, whether you get a bright band or a dark band. At the point P, what happens? The point P here, you got S1, S2 here, right? The two sources that are shown here, S1 and S2 are the two sources separated by a distance d. I mentioned some time back in the final expression that you are going to arrive at for the bandwidth, that is the purpose of the present section. To obtain the expression of the bandwidth, you will be coming across the distance d, the distance that separates the screen and the plane where you got two sources. This is the plane where you got the two light sources separated by a distance d, and capital D is the distance that separates this plane where you got two sources and the screen where you get ultimately the bright and dark bands. And what is S1P and S2P? You comment upon about the distances. S1P is greater or S2P is greater? Obviously S2P is greater than S1P. By how much it is greater? You from the point S1 you draw a perpendicular. From the point S1 you draw a perpendicular to the line S2P. The perpendicular comes and meets at a point N, right? S1, draw a perpendicular, you got N here. So what is S2N? S2N, you compare S1P and S2P. What is S2N? S2N is the additional path traveled by this light beam coming from S2 compared to the light beam coming from S1. From source S1, light goes from S1 to P, whereas from the right source S2, it again goes to P, but S2P is greater than S1P by this distance S2N. So S2N is called the additional path. This is called the path difference between the two waves or between the two light beams S1P and S2P. S2N is the path difference, right? They are very important quantity, S2P. So S1 and S2 are the two coherent sources. D is the distance between the source and the screen. D is the distance between the two sources. What I mean by small d, right? Okay. S2N is the optical path difference. This is very important. S2N is the path difference. How much is the path difference? The amount is going to decide whether P will be bright or dark. The P will be bright or dark, that will be decided by your S2N. Whether S2N is going to have a full wave or half wave and so on. X is the distance between O and P. Where is your X? X is the distance between the O here and P here. Obviously that will be D by 2 because this is the capital, this is D. So this is D by 2 and again this will be D by 2. Okay. That is what I am showing here. And so S2P minus S1P, that is a very important factor, namely so-called path difference. That is going to make a lot of sense. S1P you take it as R1 and S2P you take it as R2, which are the of different lengths as I told you. S2P minus S1P is the path difference delta. If the path difference delta is equal to m lambda, if the path difference delta is equal to m lambda, that leads to constructive interference. I told you earlier, if the path difference is integral multiple of lambda, then that will lead to constructive interference. Therefore, the m is the integer, 0 here, 1, 2, 3 and so on. M is 0. What does it mean? The path difference is 0. When will we have constructive interference? The path difference should be 0 or lambda or 2 lambda or n lambda in general. So that is a condition for constructive interference. Then you go to the case of destructive interference. If this additional path difference S2n, I showed you here S2n, if this contains lambda means what? You have a full wave, right? A full wave. If S2n is equal to m lambda or n lambda, integral multiple of lambda, you have got one full wave or two full waves, then that is the condition under which there will be constructive interference. By getting constructive interference, what do you mean? The point P will be bright, and the point P will be having a bright band. On the other hand, if S2n instead of lambda n lambda, if it is lambda by 2, then there will be leading to destructive interference. Let us have a break at this point. The rest we will see after the break. Welcome back after the break. And in this lecture, the important point that we are addressing is the following. You choose a point P arbitrarily on the screen, and you ask a question at the point P whether you will be getting a bright band or a dark band when the screen is illuminated by the light coming from two coherent sources. We are discussing the phenomenon of interference. Interference is a phenomenon where you have two coherent sources and make the light coming from the two coherent sources to interfere, to meet each other or interfere with each other. When interference occurs, as we saw earlier, you get on the screen alternately bright band, dark band, bright band and so on. You got a bright band that occurs due to constructive interference between the two light waves, or a bright band that leads to destructive interference. And for constructive interference, you know that the condition is the path difference should be multiple of integral multiple of lambda. That is a condition for constructive interference. And we saw the condition for destructive interference will be n plus 1 into lambda by 2 or lambda by 2. You can have lambda by 2 or 3 lambda by 2. That is a condition for destructive interference. Whatever be the thing, when you got two sources, when the two sources, light coming from the two sources, they interfere, you get a bright band, dark band, so on. And we want to see at a point P whether you get a bright band or dark band. And the answer to the question lies on the fact whether what happens is S2n. What is S2n? S2n, the additional path traveled by one of the light beams compared to the other beam. Compare S2p with S1p. S2p is obviously greater than S1p, right? By how much it is different? By the difference is S2n. This S2n is a very important quantity called the path difference. And I told you in the last lecture the relation between path difference and phase difference. A path difference of lambda, a full wave, corresponds to a phase difference of 2 pi. So a path difference of lambda by 2 will correspond to a phase difference of pi. That is 180 degree, right? So depending upon your S2n, magnitude of S2n is very important. That is what we are going to find now. As I told you, S2p when S1p is the path difference. The condition for constructive interference is this path difference should be lambda, m lambda. That means 0. M is 0 means 0 or lambda or 2 lambda. So the condition for constructive interference is integral multiple of lambda. So this path difference which I am showing here should contain S2n should be made up of one full wave, right? One full wave or two full waves. You got a crust here, trough here, then a crust here, trough here. Okay. The point is either you should have one full wave or two full waves or any number of full waves. On the other hand, you got a crust here and trough is coming here, then if it is lambda by 2, right? Lambda by 2 means what? You got full wave means crust here, trough here, and then the point here, right? On the other hand, you got lambda by 2 half wave here, then what happens is if you got a crust here, then there will be half wave means you will be having a trough. If you got a full wave means you have a crust here, you will be having a crust. As we saw in the earlier picture, crust meaning a crust. Or you got a trough here, then there will be trough here. The phase difference is 0, right? Or a phase difference will be lambda. So lambda or 2 lambda or 0. If the phase difference is 0 or path difference is 0, then the condition for constructive interference. On the other hand, if S2n is mean lambda by 2, that means half wave. Got a crust here, you will be having a trough here, right? You got a crust here, you will be having a trough here, leading to destructive interference. Therefore, if the path difference, as I told you, is lambda by 2 or 3 lambda by 2, then it leads to destructive interference. So the important point is this S2n, does it contain full wave or half waves? So the path difference, you got P here, right? So it is x minus d by 2 and Pf will be x plus d by 2. So S2p square minus S1p square, you can go through the mathematics. S2p square minus S1p square will be equal to S1p plus d square plus x plus d by 2 whole square minus d square plus x minus d by 2 whole square. The mathematics, all these things, you can look at the diagram, you can make out all these things. The d by 2, okay, you can do all these steps. S2p square minus S1p square is 2xd, or it will be S2p square will also be equal to 2xd by S2p plus S1p. We can approximate S2p equal to S1p. Therefore, the path difference S2p minus S1p can be shown to be xd by capital D. The point is, the path difference turns out to be xd by capital D. So the condition for finding a bright fringe at P is S2p minus S1p should be m lambda, as all of you know. Using this in the equation 1, you put this equal to m lambda. So xd by capital D, that is the path difference, putting that to be equal to m lambda, m is the order, then you get this is your what is d? Is the distance separating the screen and the two light sources. So small d is the distance separating the two light sources, and x is the obviously the bandwidth, the fringe width, right? X is the fringe width, and therefore you get the dark fringe occurs, as I told you, when the path difference is lambda by 2 or 3 lambda by 2. The condition for the dark fringe, for the point P to appear dark, is the path difference should be m lambda by 2m plus 1 to lambda by 2. Using equation 1, you get your xd by d, the same thing that you got here, should be equated to the path difference 2m plus 1 into lambda by 2. That is what you get now. So this is the condition under which the point P will appear to be dark. The first dark fringe occurs when the path difference becomes equal to lambda by 2. When m is 0, we get the first order dark fringe. So the mth order dark fringe occurs when xm into m lambda by t by small d will be equal to this much. The m plus 1th order dark band, the fringe will occur at this for this condition. The fringe separation beta, what is beta? Beta is the distance that separates the two fringes. What is xm? Xm is, you can see the screen again, xm is the point where you get the mth band. From the origin you get the mth band. So you got m plus 1th band or m minus 1th band here. The distance separating the two successive bands is what I am talking about now. That will be xm plus 1 minus xm. Xm and other things can be measured using a microscope. That you will be observing the bright dark band. You can use a microscope, so you can observe the bands and measure the distance separating the two successive bright bands or dark bands In both cases, it will be so-called bandwidth beta. Beta becomes equal to lambda into d by d. Okay, that is the final expression. So it has been colored to show that the bandwidth beta will be lambda into capital D by small d. The fringe width beta is independent of the order of the fringe, whether you have the mth band and m plus 1th band, a bright band or dark band. The distance that separates the two bands, two successive bands, is called bandwidth. It is directly proportional to lambda. Obviously, these things can be seen from the mathematical expression. The fringes produced by red light are less colorful compared to those produced by blue light. They are not very important points. About the fringe width, beta is proportional to capital D, that is obvious, proportional to lambda. The farther the screen, the wider is the fringe separation. The fringe width is inversely proportional to the distance between the two slits. This expression that you obtain for the fringe width is very important because of the fact that this allow you to determine the unknown quantity lambda. You know, in the laboratory, D can be measured easily, right? What is D? The D is the distance separating the screen from the plane containing the two sources. There is a plane containing the two sources. The screen is here. The capital D. Capital D will be like 1 meter. You have a Fresnel biprism experiment. You will be doing the, you will be using a Fresnel biprism to obtain the coherent sources. From a sodium vapor lamp, you use a biprism that we will be seeing in the lectures to come. You will be using a biprism to obtain the coherent sources, and the distance that separates the coherent sources from the screen will be roughly, that you can adjust, that will be nearly 1 meter. This will be, D is a thing that should be carefully determined, that is the distance separating the two light sources should be carefully determined. So this small d, capital D, they can be measured at ease. On the other hand, the distance separating the two bands again is to be carefully measured by using your micrometer screw. Using a microscope, you can see these dark and bright fringes. But the point is, lambda is a thing, the wavelength of the source. You got a wavelength here, a light coming from the white light in the order of Vibgyor. The wavelength is a thing that cannot be measured easily. So the wavelength of the sodium vapor lamp, the aim of the experiment is to obtain the expression of bandwidth. From the bandwidth, you try to obtain the very important and very difficult quantity, namely determining the wavelength of the sodium vapor lamp. What is the wavelength of the sodium vapor lamp? I gave you in the lecture 5893 angstrom unit. What is 1 angstrom unit? It is 10 to the power minus 8 centimeter. So the wavelength is something, it is order of 10 to the minus 8 centimeter, right? The sodium vapor lamp has got a wavelength of the order of 5893 angstrom unit, right? Sodium vapor lamp emitting wavelength of 5893 angstrom. What is 1 angstrom? 10 to the power minus 8 centimeter. That cannot be easily measured in the laboratory. This is an important experiment using which you determine the wavelength of the light wave coming from sodium vapor lamp. Whether it is sodium vapor lamp or any other monochromatic source, the wavelength can be determined by the experiment which we are doing now, or the theoretical expression that we have got now for beta. One can obtain the your lambda. Let me now pass on to the summary session. It goes as follows. Employing the conditions for constructive and destructive interferences, we determine as to whether at a given point P on the screen you get a bright band or a dark band. Finally, we obtain the expression for the fringe width or the bandwidth. To test your knowledge, let me ask the following questions. What do you understand by wavefront division in the Young's double slit experiment? The question number 2, give the conditions for constructive and destructive interferences. Question 3, what is meant by path difference? And lastly, question number 4, give the expression for the bandwidth. With this, we come to the end of the lecture number 15, and the rest of the things which are to be covered in the syllabus will be dealt with in the lectures to come. Thank you.